Hello viewers, my name is Macmilia Ariku James. You are on to Akimo's Educational Services for the online lessons. I'm going to be your instructor for physics. I'm going to take you on the topic thermal expansion in solids. This topic is majorly for the SS1 students. I know that for you in SS2 and SS3, it's going to be a benefit to you. So I implore you to listen. I like you to bring your calculator along so that by the time we'll be doing on the calculation part of it, you will not be left behind. Alright, as we have on the board, we're going to take a brief recap on work, energy and power. We have done that before now. You know very well that work is actually done when a force applied to a body makes that body to move a certain distance. If there is no distance moved, work is not done. And then we know that work mathematically is equal to force times what? Distance. This is the force that is making that body to move a certain distance. And the unit of force is what? Newton. While the unit of distance is what? Meter. That makes our unit for work to be what? Newton meter, or what we call the joules. What is 1 joule? 1 joule is the work done in moving a body one distance when a force of 1 Newton is applied to that body. We move on to energy. Energy is the ability to do work. It is the capacity to do work. And we also go into power. What is the unit before then? What is the unit of energy? Energy is measured in what? In joules, which means that our work and energy has the same unit. What is power? This is the time rate of doing work. Alright? How long or how short work is done is what we actually call power. And since we have said that work is measured in what? In joules, and our power in our time in seconds, it therefore means that power is measured in joules per second. We go to the next point, which is what? Heat energy and forms of energy. We have talked about energy. We have different forms of energy. We have chemical energy, we have heat energy, we have light energy, we have electrical energy and the rest of them. But we are going to be looking at heat energy. That's why we will be talking about thermal expansion. When heat is applied to a body, there are some things that change there. It can either change in the length or the volume. Take for instance, if I have a piece of your tin milk now, I can actually use a hammer to hit on it and deform its shape. I also can introduce heat to it and can also do what? Result in deformation of shape. So for now, we are looking at these changes in the dimensions of a body when heat is applied. What is thermal expansion? Like I have just explained, thermal expansion is the increase in the size or volume of a body when heat is applied to that body. Of course, there are some advantages and disadvantages of thermal expansion. What are the advantages? First of them, you know very well your alarm clocks or your automatic alarms. This uses the phenomenon of thermal expansion. This is actually constructed in a way that when the body becomes hot, it touches the sensor part of that circuit that begins to beep your alarm. So you see that thermal expansion is very beneficial to us. The second advantage of thermal expansion is in our bimetallic thermostat. Let me write it down. This is actually a device that regulates temperature changes in a circuit. And this is useful even in a refrigerator. So many electrical appliances actually use, even your pressing iron uses the bimetallic strip that helps to regulate changes in temperature. We have, like I've mentioned, your refrigerator. And then, we also go into the second or the third advantage. This is in riveting of metal plates. When metal plates are joined together, expansion is used in this. And then we also talk about the fitting of metal rings. Very well, especially in the construction company. when you have metals that are to be fitted together like your riveting, and you have them to be in different shapes or sizes, expansion is being used in how each of these metals is heated so that they can easily fit together when hot. When they become cold, we have so many of the strips that we have together that are made up of metals. That will take us to the next one, which is actually the high point of this topic: linear area and cubic expansivity. Alright, we have talked about expansion, and expansivity is actually the process or this phenomenon. Alright, linear expansivity. What is linear expansivity? It is first denoted by the symbol alpha. It is the fractional increase in length per increased rise in temperature. I take that again. Your linear expansivity is a fractional increase in length per degree rise in temperature. Alright, we start with the first of them, linear expansivity. What is linear expansivity? It is the fractional increase in length per degree rise in temperature. Or you may want to say it is an increase in length or that's the original length per degree rise in temperature. Let me put that mathematically. We use the symbol alpha for linear expansivity, and it is written as increase in length all over the original length of this material times the temperature rise. So let's say we have a metal that has length L. After the temperature has been increased, of course, by heating, this body expands to a particular length. And let's say if from here to here is L, it means that from L1, from here to here is going to be what? Our L2. Our L2, we have defined linear expansivity as an increase in length per unit length per degree rise in temperature. I take that again. Your linear expansivity is an increase in length per unit length per degree rise in temperature, what we call a fractional increase in length per rise in temperature. Okay? And I said if we have a body that has the length L1, and after heat is introduced, this body increased to another length, and we want to call that L2. How do we put this? Your linear expansivity is going to be your L2 minus your L1 all over the original length, which is what? L1 times the temperature difference, that's theta 2 minus theta 1. This is theta 2, this is the new temperature, and this is theta 1, the original temperature of that body before it was introduced. And you know that your temperature, of course, is measured using your thermometer. Okay, so take note of this. We're going to be using this formula when we are doing our calculations. We move on to the second of them, your area expansivity, or what we call superficial expansivity. What is superficial expansivity or area expansivity? Take note that the first one was the increase in length. For your area expansivity, this is the increase in the area or dimensions of a body per area rise in temperature. That is, we also denote this by the alphabet beta. B, this is going to be your increase in area all over the original area of this body times the temperature rise. So if you have a body whose area is A1 and heat is introduced to this body and it becomes of the dimensions A2, how do we now measure the area expansivity? We just put this as your A2 minus your A1 all over what? Your A1 times what? Theta 2 minus your theta 1. Again, your theta 2 is the final temperature of that body after heat has been introduced, whereas your theta 1 is the original temperature of that body. So we have our beta to be equal to this. Please, again, I say, take note, this is the second formula, and we'll be using this during our calculations. Then we move on to cubic expansivity. Just like your linear expansivity is increase in length and your area expansivity is increase in area, your cubic expansivity, or what we call volume expansivity, is the increase in volume per unit volume per Kelvin rise in temperature. And that means that also we can say that we use the alphabet gamma, written this way, written as what? Your V2 from here minus your V1 all over V1 times what? Theta 2 minus theta 1. From these three equations, we can actually have some modifications. Let's start. Remember that your alpha is what? L2 minus L1 over L1 times theta 2 minus theta 1. Let's say that your theta 2 minus theta 1 is equal to your change in temperature. So let's do a cross multiplication of equation 1. Let's name our equations. If we do a cross multiplication, it therefore means that your L2 minus your L1 is going to give us alpha L1 in bracket theta 2 minus theta 1. And since we have said let theta 2 minus theta 1 be changed in theta, we can say our L2 minus L1 is going to be what? Alpha L1 changing theta. And if you're given a question where you are asked to find the final length of that body after heat has been introduced, we can see that from here, if we make L2 the subject of the formula, we have L2 to be what? L1 plus alpha L1 change in theta. Remember, when your L1 crosses the equality sign, it becomes a plus, and that's why we have this. So from here, we can also say that our A2 is going to be equal to what? A1 plus beta A1 changing theta, and also your V2 will also be what? V1 plus gamma V2 V1 changing theta. Please take note of these 6 equations. If you want to number them 1, 2, 3, 4, 5, and 6. This will now take us to the calculations part. Let us read out some questions to solve. Okay, looking at the board, we have a question here where we are going to apply the formulas we have derived so far. Question number 1. When 15 meters of a metallic rod is heated from 10 degrees Celsius to 110 degrees Celsius, its length becomes 15.0 meters. What is the linear expansivity of the metal? Which therefore means that different metals have different expansivities. For this particular metal, they've not told us what metal this rod is being made of. We are the ones to derive the expansivity of that metal. Remember our formula, alpha equal to what? L2 minus L1 all over L1 times what? Theta 2 minus theta 1. Let's get our parameters in place. We have our L1, 15 meters. We have our theta 1 to be 10 degrees Celsius. We have theta 2 to be 110 degrees Celsius. And then we are going to calculate our L2, which is what we are being, L2 is 15.03 meters. So let's put that into our formula. Your alpha is going to be equal to 15.03 minus 15 all over 15 times 110 minus 10. Take note that this question is given to us in meters. Many times, the question will be given to you in centimeters or in millimeters, and you should apply your conversion factor here. For this question, we are given in meters, so we use it directly. So we have 15.03 minus 15. It's going to give us what? 0.03. All divided by 15 times what? 110 minus 10, which is going to be what? 100. So this is 0.03 divided by 15 times 100 is 1,500. So we divide that now. 15.03 and we're going to have what? 2.0 times 10 raised to the power minus 5 per Kelvin. The unit of expansivity is per Kelvin. Please take note of that. So we've been able to determine the expansivity of this metal to be what? 2.0 times 10 raised to the power minus 5 per Kelvin. That's simple. So we'll be going to the second question. Here, the length is given to us. The length of copper is 20 meters. When its temperature is 25 degrees Celsius, the length of that material was 20 meters. We are asked to find the new length when the temperature is increased to 40 degrees Celsius. And the second question is, by how much has it expanded? You may be asking, we are asked to find L2, and now they're asking us by how much. Please, this is not money. We are talking about the difference between the first length and the second length. So understand your question. The first question here, you have to find L2. And the second question here is actually your L2 minus your L1. So please take note of that before you go into answering it. So we have, again, linear expansivity to be equal to what? L2 minus L1 over what? L1 times theta 2 minus theta 1. And remember our modified equation, we had what? L2 to be equal to what? L1 plus alpha change in, L1 change in theta. What is our L1? L1 is equal to what? 20 meters. Theta 1 is equal to 25 degrees Celsius. Theta 2 is equal to 40 degrees Celsius. So let's apply that into this equation here. Our L2 is going to give us what? L1, which is 20 plus our linear expansivity was given to us to be 1.7 L2 equal to 20 plus 1.7 times 10 raised to the power minus 5 times what? This is for the linear expansivity. Your L1 is still what? 20 times what? Theta 2, which is going to be 40 minus what? 25. Let's put that in brackets. So you're going to have what? 20 plus 1.7 times 10 raised to the power minus 5 times 20 times what? 40 minus 25 is going to give us what? 15. So punch your calculator and let's know what that answer is. So first we're going to have 20 plus, then we punch our calculator. 1.7 times 10 raised to the power minus 5 times 20 times 15. I hope you have punched your calculator. We're going to have 5.1 times 10 raised to the power minus 3. So add it to your 20. We're going to have what? 20.0051 meters. You may be saying, but this is almost like nothing, but this is very significant in the construction company. Though the difference is not much, but it's very, very significant when constructing. So we can see that our new length is going to be 20.0051 meters. We go right to the second question, which says, by how much has it expanded? Of course, our II, we have change in length to be equal to what? L2 minus L1. Let's take that up. Let's do our II. The question says, by how much has it expanded? Definitely, we know that our original length was what? 20 meters. And the new length is now 20.0051 meters. So our increase in length now.
Sorry. Please, that place was not focused. Let's do it again. So they can cut that part out. Okay.
Okay. So having finished our first question, we are going right away to the second question, which says, by how much has it expanded? The original length was what? 20 meters, while the new length is now 20.005 meters. So for us to find how much it has expanded, we find the increase in length. which is we denote by what? Changing L. And that's going to give us your L2 minus your L1, which is 20.0051 minus 20, which is definitely 0.0051 meters. So we have done justice to that question. This is for linear expansivity. We're going to do one more question for area expansivity. Take note that they all flow together. The equations are applied the same way. So if we take our last question, so if you know how to apply your formula for area expansivity, the same applies to your volume expansivity. And the question says, the internal diameter of a brass ring is 15.94 centimeters, and the diameter of a wheel is 16 centimeters, both measured at the same temperature Find the smallest rise in temperature. To which the brass ring must be heated in order that it may just slip on the wheel. Okay, understand the question first. We have a brass ring that is to be fitted into a wheel, both of them having different diameters. Okay, and they are measured at the same temperature. We are now to find the smallest rise in temperature. What is that? Our θ2 minus θ1, which is your change in temperature. But first of all, take note that this is given in centimeters, which means we are going to convert. And remember your primary school where you learned your 100 centimeters to be equal to 1 meter. So if 100 centimeters equal to 1 meter, your 15.9 cm is going to be what? 15.94 divided by 100, which will give us 0.1594. And again, your 16 centimeter will give you 16 over 100, which will give us 0.16 centimeters. Take note that this is your L1, this is your L2, your L1, and this is your L2. Let's take that again. This is the diameter of the ring, and the wheel is 16 centimeters, which means for this ring to fit into this, it must be expanded to 16 centimeters. That's why this is going to be our L1, and this is going to be our L2. What about the temperature? It's not given unto us. And we have been given the linear expansivity of that material. The linear expansivity of that material to be equal to 1.785 times 10 raised to the power minus 5 per Kelvin. Take note that your area expansivity is equal to your 2 times linear expansivity. So we can say that beta is equal to 2 times alpha. Remember that, speak out, you cut it out.
Thank you. Remove the 8.
Oh, thank
It's
you.
okay. Just
Thank you. Meters. Thank you. Alright? Your area expansivity is equal to your 2 times linear expansivity, which therefore means that we are looking at a ring. A ring does not increase in length, rather it increases in the diameter, which means we are not going to use linear expansivity here, but rather the area expansivity. You'll never be told to find the length of a circle. Rather, you'll be asked to find the area of a circle. So, which means that we are going to use our area expansivity and not the linear expansivity. Okay, we have your beta to be equal to what? A2 minus A1 all over A1 times theta 2 minus theta 1. And remember that your theta 2 minus theta 1 equal to what? Changing theta. And that's what we are asked to find here. So, from this equation we have, if beta is equal to 2 times linear expansivity, your beta is going to be 2 times what? 1.785 times 10 raised to the power minus 5 per Kelvin. And that will give us what? Pick up your calculator, don't sit and watch me. So you're going to punch that to verify that your answer is correct. Which is going to give us 3.57 times 10 raised to the power minus 5 per Kelvin. So putting that here, we're going to have what? Let's do some modifications here to make changing theta our subject of formula here. So we have cross multiply your A2 minus A1 is going to give us what? Beta times A1 times what? Changing theta, which means that if you divide both sides by changing theta, you're going to have your changing theta to be equal to what? A2 minus A1 all over what? Beta times A1. We have made our change in theta the subject of the formula. So let's impute our values. We have A2 to be what? Alright? Take note that this is your length. So we're going to again find our area. Your A1 now, what's the formula for a circle? A ring has a circular shape. So A1 is going to be what? Pi r squared or pi d squared over 4. We are given the diameter and not the radius. So either you use this as diameter or you divide this diameter into 2 and use the other formula, which is pi r squared. So when we do that, put in your values. Your A1 is going to give you, your pi is going to be what? 22 over 7 or your 3.142. So let's put that in now. We're going to have 3.142 times what? D2 is what? This is D1, which is 0.1594. 0.1594 all squared. Divide that by 4. We're going to have what? 0.01996. Okay, and also your A2 is going to be your what? Pi d2 squared all over 4. Put that into your values. You're going to have 3.142 times what? 0.16 all squared divide by 4. And that's going to give us 0.0, let's put that down here, 0.020109. Alright? We're going now to put it into this formula here. We go back up here where we can see everything clearly. So, your change in theta is going to give us what? A2, which is 0.0020109 minus your A1 0.01996 all over 0.01996 times what? Hold on. Our beta is this 3.57 times 10 raised to the power minus 5 times what? Your A1, which is 0.01996. So when you punch your calculator, you're going to have your change in theta to give you, let's put that together. Minus 0.01996, and that's going to give us 1.49 times 10 raised to the power minus 4 all over 3.57 times 10 raised to the power minus 5 times 0.01996. Take that again. 3.57 times 10 raised to the power minus 5 times 0.01996. Let's try that. This is really important. What's it is? Minus 5 times 0.01996. Times 10 raised to the power minus 5. Okay, so we have our values here. 7.1257 times 10 raised to the power minus 7. When we divide this together, we're going to have 209.47, approximately 5 degrees Celsius. So you see that we've been able to apply our linear expansivity and our area expansivity as we learned. So your volume expansivity works the same way, just flows the same way we use our linear expansivity and area expansivity. This will bring us to the end of this class. You are going to check the home page for the brief notes on this topic, and your assignment will also be included there. So you do your assignment and submit it there. For comments or questions, put it therein, and when we meet next time, we're going to trash them out. God bless you. Okay, we've talked about the advantages of expansion. Expansion also
Hold
has
on.
some disadvantages.
The volume is like Okay.
That's where I have a problem.
All right.
We have talked about the advantages of expansion. Expansion also has some disadvantages. One of them is this. Remember your bridges. Many times when the sun rays hit our bridges and these heavy trucks come upon them, pressures are being exerted on these metals that make up these bridges. So the heat from the sun causes expansion in these metals. We also see this in our railway lines. Of course, you know that your railway lines there are some gaps in between these rails, okay? And when these metals expand, they tend to block the rail poles. And so you see that your train cannot move freely on your railway lines. That is the second disadvantage of expansion. And the last of them is the one you see very well at home. When you pour some hot water into your tumbler, what do you notice? You notice that it does what? It breaks. That's because that glass that is used to make that material has expanded, and so it has lost. There's some increase in dimensions that glass cannot contain, and that's why you see this glass tumbler breaking when you pour some hot liquid into it. So we see that expansion has advantages, it also has what? Disadvantages. So you see them everywhere around us.